In this video, we're going to talk about the 7 fundamental units. Now, as students of physics, we want to be able to describe the universe that we live in. And it turns out that in order to do that, you only need 7 basic concepts. Only 7. And 7 fundamental ideas can be used to describe essentially all the things that we observe in the natural world, all the things that we see in our universe. Now, once you have those 7 fundamental units, you can use them to build more advanced concepts. And those involve what are called derived units. And I'll show you how those are built in just a moment. But let's talk about first, what are those 7 fundamental concepts that we need to be able to describe our universe? I've got them listed here. And the first one listed is length, which is a concept of size. The next one is time, which is a concept of duration. The fourth one is mass. Now, later on, we're going to very rigorously define what mass is, but right now we're just going to get by with what may be your sort of instinctual understanding of mass. I mean, you know that if I have a block of gold, it's got so many neutrons and protons and electrons, and if I have a block of gold that's twice the mass, it's got twice as many protons, neutrons, and electrons. So how much stuff, by stuff I mean protons, electrons, neutrons, are sort of things that make up matter in a universe. That's what mass is. For now, we're gonna refine that definition later on, but for now that'll do. And then the fourth one is quantity. And quantity is the concept of counting or of number. And we're going to use just these 4 ideas to build an understanding of a huge amount of the physical world that we live in. Later in the semester, we're going to add in temperature, which you may think of as sort of hot and cold. And again, these are sort of hand-waving things to help us, get a notion of what we're talking about. We will rigorously define what temperature is later on. But for now, just sort of since some things are hot, some things are cold, and we can measure that by temperature. And I think you all probably have an understanding of that, at least a basic understanding of it. Now, in semester 2, we're going to add these last 2 fundamental concepts to the mix. The idea of an electrical current, which is a flow of charge. Now, I'm sure you guys learned in your introductory science classes in grade school and high school that matter is made up of protons and electrons. These are particles that carry with them positive and negative charges. You might want to think that it should be the charges themselves that are fundamental, but here we run into a constraint of the world we live in. It's actually really easy to measure current. It's not so easy to measure charge because they're so tiny. And so we actually establish electric current as the fundamental idea rather than charge, because current is so much easier to measure. We can measure current much more precisely than we can measure charge. And so charge is actually defined in terms of current, not the other way around. And that's really a limitation of the equipment that we have available, but that's how we do it to build that framework. And then the last one is luminous intensity, and that has to do with brightness, and that is related to light, which we'll talk about a little bit this semester, but mostly next semester we'll spend a lot of time talking about light. Now, for each of these units, we need some set of standards. Now, the common use of standard in the United States is the so-called imperial system, which was used by countries that used to be part of the former British Empire. Now, most of those countries have abandoned the imperial system, but it's still actually pretty widely used in the United States. And for example, the unit of distance in the imperial system is the foot. And so we measure things in feet, and feet are sometimes combined to make yards or miles or other distance units that are familiar to people that live in the United States. But in the rest of the world, most of the rest of the world, they use the metric system, where, for example, the basic concept of length is measured in meters, and it might be kilometers or centimeters, but the foundational unit is the meter. That's the standard. And in this class, we will be using the metric system for almost all of what we do. And there's another fancier name for the metric system, and just in case you ever see it, the metric system units are called SI units. Now, SI stands for International System, but it actually was originated in France. And in France, they sometimes put the adjective after the noun that modifies, and so it would be Système International, hence SI. That's the System of International Units. But in America, we usually just call that the metric system. Now, we have to have some standard of units, whether it's the metric system or the imperial system or some other kind of system. But why do we need a standard? Well, we need one for communication. Now, you guys might have heard of the story of Noah and the ark from the Bible, the Old Testament, where Noah gathered up all the animals in the world by 7 or by 2, depending on what kind of animal it was, and stored them in the ark. And God commands Noah to build the ark, which is basically just a large box that floated. And the ark was, according to the Bible, God called for Noah to make the ark 300 cubits by 50 cubits by 30 cubits. Now, what the heck is a cubit? The cubit is defined as the distance from the tip of an outstretched middle finger to the bottom of the elbow. Basically, it's the length of your hand and your forearm together. And so that was a standard unit of distance in the ancient world for a long time. And it was a terrible standard. Can you see why it's a terrible standard? Imagine you wanted to have an addition built onto your house. And so you call the contractor and you say, I want you to build this addition onto my house, and I want you to make it 60 cubits by 40 cubits or whatever it is. And you go on vacation and you come back and you see that the contractor started building the room and it's half the size you're expecting. And you go, what the heck's going on? Why is the room so small? And he points to his niece, who is like 6 years old, and says, well, we measured the distance from her elbow to her fingertips, and we used that for a cubit, and that's what a cubit is, and so, hey, it worked out. Well, maybe it didn't work out. But in any case, people's arms are different lengths, right? So that's a terrible standard. We need a standard that is well-defined. So we're going to start with the second. Now remember, the second is the standard unit to denote the passage of time. It's the idea of duration. Now originally, the second was defined as 1/86,400th of a mean solar day. The mean solar day, that's basically the time it takes the Earth to make one complete spin around its axis. And we know there are 60 seconds in a minute, there are 60 minutes in an hour, and there are 24 hours in a day. So if you multiply all of that together, there are 86,400 seconds in one day. So 1 second is 1/86,400, that fraction of a complete day, 24-hour period. Now there's a problem with that definition, and the problem is it turns out the Earth is actually slowing down over time. You guys know that the Earth is 24 hours long. During the time of the dinosaurs, it was, like 16 to 18 hours, depending on where you were in the timeline. The day has slowed down and it continues to slow down. So defining our fundamental unit of time based on how long it takes the Earth to spin, it's not the best standard. So now the second is defined as the duration of 9,192,631,770 periods of the radiation caused by the transition between two specific hyperfine levels of the ground state of the cesium-133 atom. Wow, That's a mouthful, isn't it? Basically, all that means is that this particular kind of atom, cesium-133, can emit light of a particular frequency. And so the electric fields that make up the electromagnetic wave are vibrating back and forth at a particular frequency. And we're counting as it goes back and forth, and we count out this many vibrations of that electric field in the beam of light, and however long it takes for that particular beam of light to vibrate back and forth that many times, that's how long we say a second is. Now, why did they pick this crazy number? Because that's what corresponds to the old standard. And so that's how many vibrations of light it takes to make the time of the originally defined second. And so, but now, this is not something that changes. And you can set up an experiment in a lab. You see here is actually an atomic clock. It's the sort of the device that can be used to make this kind of a measurement. And we can very, very precisely measure the duration of time using this standard. And so the second is defined now in terms of something that won't change. You know, the rate at which the Earth is spinning is slowing down. So it's a terrible thing to use to define the second. But this, as crazy as it sounds, it's something that can be set up and measured in any lab in the world. You just have to buy the equipment to do it. And then you have something where the second is rigorously defined based on fundamental things in nature that do not change. Now, the next thing that we want to look at is the meter, which is, of course, the standard of length, distance. Now, originally, the meter was defined as 1/10,000,000th of the distance from the equator to the North Pole along the meridian, that is the longitude line, passing through Paris. And so basically it was you take the distance from the equator to the North Pole via a longitude line and divide that by 10 million, and we can say that is a meter. Now, later it was defined as the distance between two transverse parallel lines. That basically means that they took a bar and they cut a lines across the bar and they measured the distance between those lines and they said, okay, that's going to be the meter, the distance between those lines. Now we had to be careful. It's specifically defined in terms of being at 0 degrees Celsius, because what happens to a bar of metal if it heats up? Usually it's going to expand, right? That would change the distance between the grooves you cut on it. And so the measurement of the meter based on these grooves had to be made at very controlled temperatures and very controlled pressures and things like that. So again, not the best standard, just because you could, have error introduced by what the temperature in the room was and, how it changes over time. Even though this bar that they used was made out of very stable platinum iridium alloy, it was not the best choice to use. One of the things you may have noticed in the picture in the previous slide was the shape of the bar. It had this kind of weird X cross-sectional shape, and that has to do, again, we're trying to minimize errors in these measurements, and that minimize the effects of torsional strain during the length comparison, sort of twisting effects on the bar. And so all these things were to try to make this standard as good as it possibly could be so that everybody could bring their own standard meters in every country in the world and test it against the prototype standard meter that was kept in Paris. But of course now we have a much better technology that enables us to measure the length of the meter much more precisely, and in terms of fundamental constants that don't change. Currently, the meter is defined in terms of the speed of light in a vacuum. And that means when there's no matter present. So it's not going through glass or air, it's just going through empty space. And it turns out that the speed of light through a vacuum is a fundamental constant of nature that does not change. And so currently, the meter is defined as the distance that light travels in a vacuum over a time interval of of 1 over this many seconds. If you think of this number not as a fraction, but just as the number that you see in the denominator, that actually defines the speed of light in a vacuum to be that many meters for every second. And so you can say that 1 meter is the distance that light travels in 1 over that many seconds. And that's literally how the meter is defined today. Now, this number is a really complicated number. Why didn't they just make it all 300 and round up? Well, the answer is because this is what is needed to make the current definition of the meter match the historical definition of the meter. They made them all sync up. Otherwise, it would have caused all kinds of problems if you just suddenly changed the definition of the meter overnight. So what we've done is we haven't really changed the definition of it so much as we've provided a reproducible standard. Again, anyone in the world can buy the equipment necessary to set up an experiment to measure out the fundamental distance of a meter, and then they can compare all their meter sticks to that and make sure that their meter sticks are actually a meter and not some other distance. The next standard unit is the kilogram. Now, the standard kilogram has also had different definitions historically speaking. The original definition of the kilogram was it was defined as the mass of 1 liter of water at 4 degrees Celsius. That is, 4 degrees Celsius is the temperature at which water is at its greatest possible density. And so that's at atmospheric pressure. And so the amount of mass contained in 1 liter of water at its densest form, that's how much mass made up the original kilogram. Now, later, they built an equivalent cylinder, again, made out of this platinum iridium alloy that is very stable, and they said, okay, this much mass is the mass that we are arbitrarily defining to be the kilogram. And for hundreds of years, that was the standard mass. That was the mass, and so different countries would send their own version of that to Paris and compare it against the actual standard mass unit to make sure everybody was in sync with each other. But that was the standard for many years. For a long time, we've been trying to replace these fundamental units, the standard by which we define them, in terms of fundamental aspects of nature rather than things that are changeable. And so nowadays, the standard kilogram is actually defined in terms of something called Planck's constant, along with the speed of light and the definition of the second, which we've already talked about. And so Planck's constant is another constant of the universe. If you've ever heard of quantum physics, Planck's constant is one that shows up in quantum physics, and it has many, many different applications to different areas of physics. But it's a fundamental constant of the universe. The speed of light is the fundamental constant of the universe, and these can be combined to define what makes up the standard kilogram. Now, measuring all these things, what's used is what's called a Kibble balance, and here's a picture over here of the technique. Now, this is a very, very sophisticated and complicated piece of apparatus, but it enables us to measure mass in a way that is based on fundamental things in the universe that do not change over time, and not some particular lump that, what if that standard kilogram were stolen? Or what if it was bombed? During World War II, Paris could have been bombed and that could have been completely destroyed. And so there could be some sort of natural disaster or whatever. So we now have a standard kilogram that, again, you can get the equipment and do the experiment, and you don't have to travel to Paris and compare to the original standard kilogram anymore. We have a standard that's based on fundamental constants of nature that literally anyone with the expertise and the equipment can measure. The next standard that we want to talk about is what's called the mole, which is the standard of quantity. And previously, the mole was defined as the number of atoms in 12 grams of a particular isotope of carbon known as carbon-12. And so we take this particular isotope of carbon named carbon-12, and we measure out 12 grams of it, and then we count how many atoms of carbon there are in 12 grams, and that many carbon atoms is defined to be 1 mole. That was the old way of doing it. And the reason they did it that way was because of things. It's a very useful definition in chemistry. But nowadays, because what is the standard of quantity? It's just a number, and it's completely arbitrary. They could have picked any number they wanted. They just happened to pick a number that had some uses with the periodic table in chemistry. And so they've gotten away from this convoluted definition, and now it's simply defined as the number it is. The mole is defined as 6.022-14076 times 10 to the 23. A mole of atoms is this many atoms. A mole of motorcycles is this many motorcycles. It's just like saying, how many motorcycles is a dozen motorcycles? Well, 12. That's the number that corresponds to a dozen. How many motorcycles are there in a mole of motorcycles? Well, there'd be this many motorcycles in a mole of motorcycles. And this 10 to the 23, you can see that's a really big number. But no matter how big it is, it's just a number. And by the way, this picture over here is showing some different substances. And I don't know what all these substances are, but the point was that the blue substance, this is how much of the substance you need to have a mole of the atoms of that kind of substance. This green substance, that's how much you need to have a mole of that many atoms or molecules or whatever it is. But long story short, what you need to know is that a mole is just this really big number, and you don't need to know all of these digits. Most people just remember 6.02 or even 6.022 times 10 to the 23rd, and that's a pretty reasonable approximation for a mole. Next, we can talk about thermodynamic temperature units, and the standard unit of temperature is the Kelvin. Now, of course, we have other units of temperature that are commonly used. In the United States, we commonly use Fahrenheit, and in most of the rest of the world, they use the Celsius or the centigrade scale for measuring temperature. And even in science, we often use the Celsius scale too. But the Kelvin is the standard of temperature that is essentially, it's a fundamental standard of temperature because it's based on absolute zero. Now, historically, the Kelvin degree was defined as 1 over this fraction of the thermodynamic temperature of the triple point of water, H2O. And the triple point, there's a particular pressure and a particular temperature at which water can exist in all three of its phases simultaneously. It can be solid, liquid, and gas all at once at that particular pressure and temperature. And so they take that and they divide it by this number, and that is how the Kelvin degree is defined. Or rather, how it was defined historically. But now, the Kelvin degree is defined by fixing the Boltzmann constant to be this value in joules per Kelvin. And that joule is an energy unit we'll learn about later on. But the point again, we don't necessarily have to know what the Boltzmann constant is yet, but what you do need to know is that this is another one of those fundamental constants of nature that shows up in physical systems. And so we can define the Kelvin temperature in terms of this fundamental physical constant. Now, again, hopefully you see the utility of this, of having these fundamental ideas based on things that are sort of built into the universe and that anyone can measure in any lab in the world as long as they know how and they have the equipment that lets them do it. Now, it is worth noting the Kelvin scale is based on absolute temperature of absolute zero. Now, we'll see later on when we talk about temperature that if, for example, you have a block of gold and you heat the block of gold up, the atoms in the gold are vibrating back and forth faster and faster as the temperature gets hotter. So what happens to the temperature of the block of gold as the temperature decreases? Well, the atoms and molecules of whatever substance it is, they vibrate more slowly. So the gold atoms vibrate slower and slower as the temperature is lowered. What's the lowest possible temperature you could get? Well, that would be when the atoms stop vibrating altogether. When you no longer have any vibrational motion at all, you can't go any slower than that. So that means that the gold bar can't get any colder than that. That's absolute zero. And so the Kelvin temperature is based starting at absolute zero, and it's defined in terms of this definition up here originally. Now it's defined in terms of this Boltzmann constant. And essentially what that means is you start at absolute zero, and this much temperature increase represents 1 Kelvin degree. And so that is how we do it. And technically, you don't actually say Kelvin degree. That's kind of a bad form, but I wanted to say that so that hopefully it would be understandable. But usually we just say it would be the temperature interval of 1 Kelvin. Okay, we're getting close to the end now, thank goodness. So the next one that we want to look at is current as a fundamental unit. Now, when you're talking about properties of matter, it's actually charge that is the intrinsic property of matter that's built into matter. You guys know that neutrons don't have a charge, protons have a positive charge, electrons have a negative charge. You learned this a long time ago. You've probably seen this lots of times in your schooling. But just like an electron has a certain amount of mass, an electron has a certain amount of charge, and that's fundamental to the electron. But as I said earlier, those charges are really tiny and they're hard to measure accurately. And so historically, rather than defining the standard of measurement to be the charge itself, we use current, which is easier to measure. And so we basically define the charge in terms of a certain amount of current contains this many charges in it, and then we can measure the certain amount of current. And so the current standard defining current, no pun intended there, is made to fix the elementary charge. That's a fancy word that describes the charge on the electron, also coincidentally the charge on the proton. That's called the elementary charge. And that's found to be this value, 1.602 blah, 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 times 10 to the minus 19 coulombs, where a coulomb is the unit for charge, and it's actually defined in terms of ampere times seconds, where ampere is how much current you have flowing, say down a wire or whatever. And last but not least, we have luminous intensity, which is a fancy word for brightness, how bright a source of light is. And the standard unit of luminous intensity is the candela, which is abbreviated usually by CD. And here's the fancy definition. It's consider a source of light emitting a monochromatic, that means just one color, a particular color with this particular frequency. That's how many times the light is vibrating back and forth. So you have this particular color, the color that corresponds to this particular frequency. The candela is the brightness that would give a radiant intensity of this many watts per steradian, where watt is a unit of power, we'll learn about later. In steradian, that's a weird unit. Actually it's a unit of angle, like radian is a unit of angle, but it's a three-dimensional angle. Think like cones. It's like the angle that makes up different cones that have different spreads in them. That some cones might be narrow, some cones might be fat. The angle of the cone can be measured in what's called a steradian. And so, and if you go around the entire sphere, that sphere would have a complete angle, a complete solid angle, they call it, of 4 pi steradians. Just like there's 2 pi radians in a circle, there's 4 pi steradians of three-dimensional angle in a sphere. Anyway, the long story made short is that the candela is roughly the brightness of a standard wax candle. Again, we have this very, very fancy definition that we designed. It looks really convoluted with these weird numbers, but we picked that definition to make it line up with an old-timey standard. And and the oldest of them using just a plain old wax candle. So anyway, again, those are how our fundamental units are defined.